University. He has about 15 years of experience in both software and semiconductor industries. He works in the areas of performance aspects of clouds and big data, and then IoT stream analysis like videos and security. Today, he is here with us to talk about performance measurements analysis and tools and techniques. So over to you, Professor, for the continuing the lecture.
Thank you for this kind introduction, and thank you. I welcome all of you to this talk on performance analysis and tools. Um, let's try to make this as interactive as possible. Please feel free to message. I'll stop and ask a few questions, and you can make sure that both you and I are still awake because it's a longer session. So this talk is actually divided into two. The first part of the talk we're going to be talking about is the first half, about roughly an hour plus. Where we're going to be talking about things, the methodology itself. What is performance? Why do we really need to measure performance? We will be talking about workloads. What do you mean by workloads? And what do you mean by benchmarks? Then we talk about what metrics are we interested in. And when you're talking about performance, what should we be measuring? What should we be working with? Then comes the question of simulators. I think one of the people in one of the students had this question: what's the difference between simulation and modeling? And I will try and touch upon that. We tend to use the two interchangeably, but hopefully I will try and clarify the difference between the two. Okay, then that's the first half of the talk. But performance and tools are something which are not, very cleanly separable, right? So, so you can see already that simulator is a tool, modeling is a methodology, and what we do here is we will talk a little bit about simulators now, but then we will go about talking about things like how do you profile programs. How do you figure out how much CPU it's consuming, how much memory it's consuming, what tools are available, what techniques do these tools use? Not only it's important to understand what tools are there, it's also important to understand what techniques these tools uses so that you can be aware of what you're measuring. We'll be moving then into the software part of things. We'll be looking a little bit at operating system activity. And then we'll be moving on finally to looking at how do we really measure microarchitectural activity, because a lot of this workshop is about hardware. How do we design hardware for the future? So this is what we will talk about today. And in the afternoon in your lab, it's the second half of it which we will be more focusing on the tools part. Okay, so just to kind of set the context, here's a small quote. This is attributed to Lord Kelvin. It says, when you can measure what you're speaking about and express it in numbers, you know something about it. What it really means is that if you really understand, if you really want to understand computer architecture or microarchitecture, we need to understand the performance in a numbers way. To understand whether or not a particular cache is doing well, whether or not we are going to fetch in. So we discussed a lot about superscalar architectures on day one, and then caches. So how do you know the cache is effective? How do you know how to right size your cache? All of these are questions which can only be answered when you have some way to measure what you're trying to do. And that's really is this crux of today's presentation, where we're going to be talking about methodology to measure and methodology which goes about in trying to in building hardware. Okay, so just to give you some background on how a processor is manufactured. From the time a processor, you start architecting the processor. We studied about the core of the processor, which is the CPU, the pipelines, and then putting all these cores together, we need to have an interconnect and the cache and the DRAM. We put the SoC together, and once we put the SoC together, we manufacture the silicon, which means that is when the silicon is actually, the die is actually prepared, and then we need to verify and validate whether this die is actually meeting up. We need to test it to make sure that it works properly. And only when we are completely confident that there are no bugs in it, or which is manageable, we get to this part where we release it to market. So there's some parts in terminology which are called pre-silicon. Pre-silicon is the part when before the die is manufactured, and post-silicon is the part from which you actually have a physical piece with which you can work. Okay, until this part of it, there is no real hardware. There is no hardware. Everything is on design on paper. What we do is we have to construct what is called RTL. So this is when RTL is constructed, and after the manufacture of the silicon, this is translated to hardware. So this is the process by which, and this whole process takes pretty much a few years. You can say 2 to 3 years. From the time you conceptualize a design and from when it is ready to release to market. Now, it's important for us, and most of you who go about buying, a processor, you're really worried about whether this processor is going to, the machine is going to perform or not. This, at the back of your mind, that I really need to make sure that the processor performs to my expectation. Okay, so now from this point onwards, the challenge is really from this point onwards to this point. Here, there is no hardware where the design is being conceptualized. So you need to conceptualize the design. And from there, you convert it to RTL. This is the implementation of the design. So in all of these parts, we need to ensure that we have to do various things. Like, for example, when we are conceptualizing the design, we have to evaluate alternative design. Should we have a write back cache, or should we have a write through cache? Should we have, how many cycles does it take to prefetch from the cache? What should be our prefetching algorithm? How do we conceptualize and how do we evaluate alternative designs in order to design our processor, the core of the processor, the pipeline? How do you know how many floating point units you should have? How many units you should have? So we need to be able to estimate the performance of the processor at that time. One is we need to pick alternative designs. Once we have picked the alternative that's going to go into our product, we need to estimate performance under various situations. So at this point, we are estimating performance. Here, we alternated. This is the place where you're looking at alternative designs. Once we have frozen on the alternatives, we have to estimate its performance. Once we estimate the performance, when the die comes back, we have to verify that our performance goals are met. If there is a performance, escape at this point, something goes wrong, we need to debug the performance issue under real-world scenarios. So this is the issues that we get. Sometimes the customers will say that we need to, it's not really working the way we want it to work. Then you need to go and debug it. So performance in when you're looking at performance of a hardware, it starts all the way from pre-design to after the customer receives the part. Any questions at this point? You can also feel free to unmute and ask your question if there's a. Okay. None, then I will move on. Okay. So the question then is, what's the general methodology that we use for doing this performance evaluation? The first step is actually selecting an application. So you're going to study something, or rather I would call it selecting a workload. So we want some application, some workload that we select, and how we select that is what is left a little later. We'll come in that. Once we select the workload, we will execute it on either the hardware, if the hardware exists, otherwise we will execute it on a model of the hardware. Just like the way we, when we don't have the hardware, we have to do something, right? So that's when we have to build a model of the hardware and build and run it on this. This we have different choices of what we can run it on, but right now just assume that it's just some kind of model. As we execute it on the model, we first have to identify what's our metrics of our use. What should be our metrics that we need to pick? Then we collect these metrics and then analyze to see whether, what our performance goals were, are we meeting those goals or not? And if not, why are we not meeting those goals? A key challenge here is repeatability. If I'm running the application and the workload again and again, I must get results which are multiple iterations must give me results which don't have too much variation in them. Like for example, if you're running things at the RTL model, your variability will probably be less than 0.1, less than 1%. Okay, that is the kind of, if you run it multiple times, you should get less than 1% variability in your results. Okay. Otherwise, you're not really sure what's going on. If you're running it on the OS or this, you can get about 10% variation. But 5 to 10% and less is what we should kind of aim for in order to make sure that whatever we are studying is indeed, it's not because of some noise that you're getting it. It's because of the behavior of the program itself, or behavior of the hardware itself. So having kind of looked at why we need to look at performance, the next step that we need to look at is how should we be selecting these workloads? So any ideas about how we should go about selecting these workloads? Any thoughts? Please feel free to type into the chat.
There could be some metrics. How many times that application needs to access the memory, or that instruction access the memory, kind of thing.
Let me just note down here. So you're saying based on architecture, usage of program, right? That's one choice. Okay.
Other can be like workloads would be based on like what is the power, at what power it is working, and what is the temperature currently that core having, so that it can pick up that workload.
You're looking at power related. Okay. Then there are standard benchmarks. I see this on this standard program standard. So this is also real world applications. Anybody else wants to take a shot at it?
Tested to the worst cases.
Okay, so what do you mean when you say tested to the worst cases?
That basically try to overload the processor and the memories to their highest extent.
Overload. So these would kind of be stress tests. We're looking at stressing this scenario, right? Okay.
I think it also depends on what we're trying to measure. For example, if we're trying to measure the performance of, say, the cache, then we have to maximize the locality in our program and try to measure the performance of the cache. Or depending on which aspect of the computing system we want to measure, we can, accordingly design different software.
Okay, good. So we've got a very good set of things to go with. So let me kind of go with traditionally how did people start, very interestingly. So the first kind of, we use the term workloads and benchmarks a little bit interchangeably, but there is a subtle difference between the two. A workload is anything that would execute. A benchmark is generally something which is standard. People, a standard workload is a benchmark. Okay, but I would kind of, for now, I'm going to use the terms interchangeably. So workload that we're going to select, the first one is what is called a synthetic workload. And what is the synthetic workload? Where did it start from? People said, hey, if I take, for example, Whetstone and Drystone. These are two very standard, benchmarks. What did they do? The Drystone author, he analyzed the instruction mix of various real-world programs which were available in those days. This was in pretty much in the 80s. He analyzed the instruction mix and said, can I create a synthetic program that will have the same instruction mix as many of these real-world programs? Okay, so the program really does nothing. If you kind of look at the program on the right, this is a snippet from Drystone. Okay, it really is doing nothing. It's just doing some record, copying something from one record to the other, going over a pointer. Essentially, it's just mimics the instruction set behavior or the how instruction sets are being used by a set of real world programs. Unfortunately, Drystone and Whetstone, the difference between Drystone and Whetstone is Drystone is more integer focused, whereas Whetstone is more floating point focused. So it kind of mimics the floating point behavior of many real world applications. But these are very old. First, extremely old. They are, like you can see, 20, 30 years old. So they're probably no longer representative. There's also the challenge of, what some of the people used to report how much Drystone number they got. Now, Drystone also reports a number saying that this is how fast it ran, or this is how many times, gives you a Drystone number when you run this. So this tells you how fast it ran on a particular architecture. Now, because this kind of a behavior is never exhibited by any real world program, what people started doing was use a compiler which understands this particular code and knows that this is, I'm compiling Drystone, and it kind of optimized everything out. So you got extremely good scores. So this is, the caveat is this is really bad to use. It's good only because people have been using it for the donkey's years, but otherwise, this is not a particularly good program to understand. And it's very small, so it fits in the L1 cache. So it's only testing your CPU pipeline. That's all. So it's a measure of your CPU pipeline's efficiency. Single thread performance. It's also single threaded. So these are all the challenges. It's single threaded. It's running very small, so it fits in the instruction cache. It fits in the data cache, so you're not going to see any cache misses. It's not stressing that part of the the entire SoC itself. So that's the challenge of using a synthetic benchmark. Now, what's the next thing people did was they took that observation that if I look at some of the standard programs, I know that 20% of the code is responsible for 80% of the resource usage. Right? This is standard. Most programs, that's the whole reason why caches work. Caches work because there's a small piece of the code which is responsible for more than 80% of the time that is spent on it. So why can't we extract that kernel? We compile that kernel, run the kernel. If that kernel runs well, that we know that this particular architecture will run well. Okay. Standard examples of these are Livermore loops and linpack. Examples from linpack, what's happening inside is DAXP. The DAXP kernel is nothing but double AX plus Y. or dot product with double precision, AX plus Y, okay, which is trying to do that. Just give me a minute, please. Okay, so when we do this, what we are doing now is just like the way once you mentioned, we are going to be stressing only the floating point unit, but this is somewhat more realistic because this is actually being used by some real programs. And traditionally, these kind of kernels came from high performance computing applications, programs that were doing fluid dynamics, or programs that were doing molecular simulation. All of those from the physics and the science world of science, which needed a lot of computation. These kernels were extracted from programs that were running there. So these were also good, but again they suffered from the very same problems. They suffered from the problems of it being single-threaded and the fact that it doesn't really, it fits very much into the cache. So it's pretty small. It gives you some measure of performance. But now the question that we really want to ask is, when we select these workloads, is the following. When we are architecting a processor at this point of time, are programs that we should be using to define the performance of our product, and then we release it to the market. So this is where the customers actually use the product. Between the time at the time of design, if you select kernels and if you select workloads that are not representative of what the customer will be using, then the chance that you will be able to build a processor that will be able to run at the customer site and perform to the customer's expectation, those would be unlikely. So we should make sure that our workload selection is representative of what the customer will use. So hence, we look at the next type of workload, which is really getting some kind of real applications into it. Okay. So this must be representative of what the customer will run on the hardware. So examples, and this, they are standard, again standards here. People have looked at some of the standards. For example, spec. Okay. It's a consortium which looks and which its job is to make sure that it builds. One of the tasks that the spec consortium has is to make sure that it releases a workload specification that is more representative of what application programmers would run. I'm just giving you one particular spec, CPU 2017. This is only a CPU focused benchmark. There are other spec benchmarks also. In 2017, this consists of 43 benchmarks. Very often, most hardware manufacturers will use the spec numbers to define what kind of what kind of performance their part will have. So you will find that in this there are 4 major suites, but I'll kind of specify. There are 2 variants of each one. So there's an integer rate and an integer speed. There's an integer benchmark which is there. The integer benchmarks contain things like GCC. Compiling GCC by GCC itself is one of the benchmarks. Then the other benchmarks are things like MCF. There are a bunch of other benchmarks. There's some AI benchmarks. This is route planning, MCF. So multiple algorithms which are used, they are converted into this. Floating point benchmark, for example, NAMD, molecular dynamics. So this is, there are a bunch of both of these together. There are about 43 such benchmarks, workloads which are there. This doesn't really cover things like, database processing. So when you want to run databases on your hardware, for example, Oracle, or you want to run MySQL server on your database, you need to be looking at something different than what, not in just integers and floating point, but you want to be looking at how does it handle transactions and stuff like that. So this is what comes from the TPCC benchmark, which is the TPC, which looks at transaction processing kind of workloads. Typically, these have been the applications that have been used for workloads. What we also see is with new emerging workloads, suddenly we see this new, with the birth of Google's and Amazon's of the world, the cloud has developed. We see a lot of new types of applications which have developed, like for example Hadoop or any of the big data workloads which have the nature of having a large amount of data being accessed, or cloud-based applications like for example microservices or FaaS. These would require us to think about new workload suites that our customers will be running on. So the customers will be running on something, they might be running some cloud applications. So how do we make sure that we test our hardware and design our hardware such that it will run well on the cloud? That's going to be a topic which I will touch upon next week during the advanced session when we talk about how new workloads are emerging and what impact they have had on architecture design. The final type of benchmark that we are going to look at is what are called micro benchmarks. These are targeted applications. Like you mentioned, suppose you want to test only the cache. You want to study only the cache behavior, or you want to study only the prefetcher behavior. Then how would you design a small benchmark that only tests that aspect of the behavior? Okay, so you would write a small program, and that small program would only test, let's say, network performance. Whether you're able to, there's one called NetPerf, which allows you to study only networking performance. This is another one which is called Stream. Stream basically does just sequential writing and reading, and it's very useful to run Stream and get a feel for how your caches are performing. So these micro benchmarks are very commonly used and people write small micro benchmarks targeted to study different parts of the behavior of a particular application. So we started from essentially for the 4 types. So what you guys kind of put down, we talked about standard benchmarks, real world applications. These are spec. We talked about this aspect, which is power and aspects of computing systems. We look at these as micro benchmarks. The ones that we haven't talked about are stress and worst case. These would also be typically covered by micro benchmarks, where you write specific benchmarks, specific workload to do overload the system, test it under worst case scenarios. Any questions, anything that you want some clarity on until this point? Yeah, so question from Gautam, wouldn't the workload change based on what we want to measure? Like for example, for peak performance, for sustained performance, power efficiency. So they are, it's a very good question. Yes, our workload would depend on that. There are 2 types that we generally need to take when there are 2 reasons why we tend to do pick workloads. One is we tend to pick a standard workload, like for example spec, or for example we have something like TPCC, because that is what the market demands. When you want to sell a processor in the market, you're going to be able to, you want to be able to compare your benchmark against a benchmark which is your processor product against, let's say, ARM wants to release a product, and ARM needs to measure it against Intel. Okay, then how would ARM and Intel kind of compare? You can only compare if you have a benchmark. You have to run very much the same benchmark on both processors and report the score. And that's how you can say how good your product is when compared to the competition. So the market forces demand that you use some standard applications, right? And how would you ensure that your program does well, your standard benchmarks do well on your architecture? You can do that only when in your design process you have considered these workloads when you're doing your design. Okay, that's point number one. The second part that you want to do is, yes, but however, there are many scenarios where we want to look at only one specific aspect of our hardware. We want to look only at the cache memory, how well it does in the cache memory. In such cases, it's very important, or power, for example, it's very important to have micro benchmarks that will only look at that aspect. Sometimes micro benchmarks are very, as a tool, it's very common to use both in academia and in industry. And those are not very, for most companies, they will keep these, they'll not reveal what micro benchmarks they're running because that's really how their internal processes are. There are some standard micro benchmarks which you can always use. Okay, there was one more question which came along which said, how critically do companies test for hardware security? Okay, I don't want to answer that question. Do we have, because I really don't know, but I would assume that they do. Do we also have standard benchmarks for secureness? Okay, when it comes to performance, okay, performance and power, or performance and security, very often have contrasting requirements. If you want to be extremely secure, you're going to have to compromise on performance. If you want to have low power, you have to compromise on performance. So very often there is a trade-off. Okay, power and performance, there is always a trade-off. Between security and performance, it depends. If security is often not compromisable, you have to compromise performance. And that's when hardware manufacturers start to say that, okay, if I have to do encryption, let me see whether I can provide some kind of a hardware piece inside the processor which will do encryption at a much faster rate than what a standard CPU can do. Right? So that's the challenge between, there's no real benchmark for security, but you could do various things like, for example, you could run the same benchmark under certain secure scenarios and under certain, like for example, there are mitigations for all of these Spectre benchmark, Spectre, this, you could turn off the mitigation and see how well it does. The loads associated with tend to be capacity driven. What are some of the loads associated with workloads on a spectrum of handheld computing? I'm sorry, I don't know the answer to your question, because what are some of the capacitance values? Typically, to be honest, I don't know the answer to your question, because this is at a much lower layer than I would have worked at. Which way workload influence highly? Number of different tasks or number of repetition of the same kind of tasks? This is again, it's a good question. For certain things, you want repetition of the same kind of task. For example, real programs have loops. So if you are testing, if you want to kind of understand how well your processor does in terms of branch prediction, in terms of having a cache, you really need repetition of the same kind of task. You need that kind, study that. On the other hand, if you're studying a multi-core, multi-threaded processor, then you want to understand how well the workloads conflict with each other or how well they work with each other. You need it to be doing different kinds of things. So we probably need both, not or, we need and. Is that clear, Himanshu? Okay. So let's move forward and look specifically at performance metrics. Okay. Very often, the metric that we are really interested in for most part, most at the hardware level, is how fast is the application running. For many benchmarks, it will tell a score, it will report a score. For some of these, we have to measure the number of clock cycles that the application takes. Okay. Very often for hardware designers, we also look for this term called instructions per cycle. Because we have a pipeline and the pipeline is expected to produce one instruction per cycle. If it's an ideal pipeline, a single threaded pipeline, we expect this pipeline should give us one instruction every cycle. That's the goal of the design, right? Now, if it gives us less than one instruction per cycle, it's because it has some dependencies or because it's hardware is this. But assuming that it is non-superscalar architecture, it's going to give you one instruction per cycle. If you do have a superscalar pipeline, then you ideally want it to be 2 instructions per cycle. But very often you will get much less than 2, as we looked earlier, or the VLIW case. You're going to expect it to be more than 1 instruction per cycle. How much ideal case is having 1 instruction or 2 instructions per cycle if you have two-way superscalar or VLIW with too wide. But how much less than the ideal do we get? And what's really contributing to this drop in IPC? Are you not getting the IPC because you're not able to fetch instructions in time, you're not able to decode them, or missing in the cache, or because your branch predicted incorrectly? That's really the next level of detail that most of the architects want to look at. Sorry for that misspelling, I misspelled throughput. But the other one, you're interested in throughput. How many instructions? That's really throughput. How many instructions are we getting per cycle? Okay. So, like I mentioned, the 2 performance challenges that we're going to look at: A, what applications are we running, and that's really governed by what are we kind of testing it for, and B, repeatability. We want to get the same numbers every time. If you're running something, if you're trying to figure out what's the IPC, we want the same IPC. If we are going to get number of clocks, we want to get roughly the same number of clocks. Now, the question is, how really do we do this pre-silicon? If we have hardware, we can understand, we run the program, we get the result. But when there is no hardware, what do we do? And what factors does the application program depend on? So anybody for any thoughts of how do we get an estimate of performance when there's really no hardware? Any thoughts on that? Yeah, okay, so we have one thought here. So you have emulators, you have simulators. Yes. Spice. Is there much difference between IPS? IPS, I guess you are meaning instructions per second, and CPS, is that cycles per second? Parvati? this is the frequency of the frequency at which the clock at which the core is being clocked at. Okay, this is the number of instructions you can execute per second. If your instruction requires 2 clocks to run, then you will get half the frequency will be the number of instructions that you can execute. Your ideal goal is you want 1 instruction completing every cycle. Now you know that one of the challenges is that this is not fixed. Frequency is not fixed. Most of the processors today have variable frequency, or what Professor Preeti Ranjan Panda mentioned a while back is because of power reasons, you want the frequency to be moving. So if you're having a extremely CPU centric workload, which is not going to go to the cache, you can pretty much increase frequency at that point so that you can execute instructions really fast because you're not going down to cache. You can execute but frequency comes at a cost. You're going to be, the more frequency that you run at, your processor is going to become hot. So you need to, at that point, to slow down your frequency. So there's a range of frequencies that your processor will work with. So this is another factor that your application performance depends on, which is the frequency at which you're going to work. Okay. We improve simulators to get better ideas as we go on testing the architecture, like moving to test benches in Verilog, Chisel, etc. After using simulators will become more accurate. RTL simulation with this. So we have simulators. So we have multiple types of simulators. Yes, we have RTL simulators, and we have cycle accurate. I would call it. Let me call it microarchitecture simulators, and we'll get to these. Any other this? So now the question that we have is that we have a program, and we want to estimate the performance on this non-existent hardware. So to estimate the performance on a non-existent hardware, the approach that we want to do is we want to take a model of the hardware. Right? Just like the way people, if you want to look at and you want to go buy a house, people will show you a model of the house. It could be on paper, or it could be an artist's sketch. It's a model of the hardware. Now the model of the hardware could be, modeling is generally a term which is used of representing the real world using some parameters. So you could have an analytical model. Okay, many cases people use analytical models, but not when it comes to designing hardware, because analytical models are quite far away. If you want to do quick estimates, you can use analytical models. But if you want to engineer a good system, you need a model which is very, very representative of how things will work in the real world. So your two choices that you have are, you can use emulators to emulate using hardware. You can go emulate exactly how the hardware is working, or you can use simulators, which is a software technique which models the way the pipeline behaves. Okay, so typically speaking, most people, when they say when we want to look at application performance factors, this is what they will talk about: the algorithms used. For computer architects, the algorithm you need to fix. We are not going to be discussing algorithm very much in the methodology, because once the people give us a good algorithm, there's a good algorithm. The question is, how fast does this algorithm run on our hardware? So a question that we want to ask is, where is exactly the time being spent? How does it map to different parts of the hardware? Are we using some of the hardware efficiently? Those are the what kind of hardware should we put in place to make sure this application works efficiently? Those are the questions that we want to ask when, as computer architects. But if I were to just take hardware, so this is our hardware, which is basically CPU, cache, memory interconnects, and we have the application which we want to measure on. Does the application run? Do we run the application directly on hardware? How should we measure? Let's assume that this is our, let's assume we start our world famous A.out program, and that's what we want to run. And we want to run the A.out on, let me call it's the new AMD processor, which is the Milan processor, which was some time back. Can I run A.out directly on top of the AMD processor? Not a virtual machine. Virtual machine is slightly different. I mean, we cover that maybe next time, what a virtual machine is. But does it run directly on hardware? Yes. So you're right. So you start from, let's assume you start from hello world. You compile hello world using GCC, and then you get A.out. Can you now still run? Need to convert the assembly code to yes. So this contains. So there might be a hello world .s, which is your assembly code, and which is intermediate, which your compiler generates, and then from there it generates the binary which will be executed. Now can you execute the A.out directly on your hardware?
So can you tell what is available exactly? Like, do we have some Verilog codes or something?
No, we are not looking at Verilog. Let's assume that we have. Oh, you're saying here. So let's
Yeah,
assume
like what is the AMD available? Like, do we have the chip or like?
Yeah, for now let's assume there is a chip. There's a chip.
Then we need to provide the assembly instructions, right? The numbers.
Is it just we need to provide the assembly to run? Do we need anything else? So the question that I ask is, what I'm asking is, how does this A.out get loaded into memory? How does this A.out, which probably after you compile it resides on disk, how does it get loaded into memory? Yes, that's right. So you have OS, right? So you have the OS in between. So in general, for many cases, the application does not run directly on hardware. There's a huge bunch layers of software between the time your application runs and the hardware. Okay, so if we have to run this application, we need the OS and we need libraries, right? For example, math libraries, something else. We need a bunch of things. We need a loader, linker, all of these things. These are all layers of software that exist between the application and the hardware. And all of these, when we are saying that we are contributing to performance, when you are saying that you want to study the effect of these, we are actually studying the effect of the application, plus we are studying the effect of all of these software. Now comes the challenge of repeatability. If you're studying this on a chip, right? If you're studying this on a chip, then we need to make sure that all of this does not contribute to noise. I mean, there is nothing else which is running which does not contribute to noise. It's only the application's behavior that we are trying to capture when we are trying to measure this. Some part of the software is important. If you're doing some OS work on the in between, then that is important. But the rest of it, we don't want it to affect. So some of the pieces of the software stack that become important to us are at the heart at when we are doing the post silicon work is the compiler. What's the compiler we are using? How does it map the application to the hardware? If you're having a multi-dimension array, how does that get laid out into memory? Okay. Then the runtime systems, the OS, the libraries. If you're running a Java application, then there is the JVM. How does JVM behave? Now, you know that JVM does automatic garbage collection for its data. How does the garbage collector behave? Does it kind of switch the memory that behind the scenes? Does it do some change the memory that you are using? So how does this work? There are a bunch of other things that the operating system brings complexity and to the entire thing. How do you interact with the OS? Like, for example, when you need some resource, you want to read some data from a disk or something, then you voluntarily ask for resource or you want for more memory. These are cases where you need resources, you're asking the operating system for some work. Sometimes there may be interrupts, or you may have a context switch and you may move to a different application. Even these add to the complexity of measurement at the hardware level. Okay, now performance can also depend on other applications, the hardware components that you looked at. For example, the TLB. So you know that TLB misses could cause paging to happen, which also is because of the additional complexity that comes in because of the operating system. Now, all of these, somebody mentioned virtual machines. These also add a lot in terms of this expanding this software stack in between. It's continuously adding more pressure. Like, for example, virtual machines or containers or fast models, all of these are adding more pressure. And this we will not be looking at now. So what we will try and look at is we will only try and look at some aspects of the OS, some aspects of how to measure application performance, and on hardware to look at microarchitecture. Okay, now very interestingly, which I did not kind of put down, there's one of the questions that came along was, hey, is this really running on a chip or is this running on a model? Right? Model could be a simulation model or an RTL model, in which case we would be running something very different. And I will come to that when we talk about simulators. Okay, so now comes the question of repeatability. If we need to study application performance in a repeatable way, we need to fix all of these other environments, all of this intermediate things which are there. This needs to be fixed. We can't be changing the operating system version number or the libraries or whatever else is running on the system. We can't be changing that. We have to make sure that between two runs, these are exactly the same. So otherwise, we are not going to get repeatable results. So in order to ensure repeatability, we have to kind of go this path of making sure we freeze this, these components. Okay, like I said, IPC itself is not enough. We need more details. Like, for example, we want to understand how the branch predictor works or how the prefetcher works. In such cases, if we are doing it directly on silicon, then the silicon contains certain hardware counters which we can read, and we can figure out what, how many times did the branch taken, not taken, all of this, there are counters there. If not, we have to use simulators. If you're doing in pre-silicon work, we have to use simulators and emulators to figure out how well this performs. Okay. Any questions at this point? Anybody? Any questions? Okay. So what we've looked at so far, we've looked at the choice of workload selection. We've looked at what different metrics that we want to look at. And we want to look at simulators. Now, one of the key things that we generally tend to look at, when we tend to look at stats at the level of branch predictors, we do not, if you see most academic literature and even work which the industry does, if you look at things like cache miss percentage, L1 cache miss percentage, L1 cache hits, the counter will give you the total number of hits that it took from the beginning to the end. Your simulator will give you the total number of misses from the beginning to the end. Now, if there is some operating system activity in between, slight amount of operating system activity or something, and your number of instructions that execute change is not the same every time. It's not going to be exactly the same every time you run. It's going to be slightly different every time you run your application, right? So how can you compare misses directly from, one where there are some more instructions executing and one where there's slightly less number of instructions executing? One technique is to use, you can use miss percentage, but very often in the literature what you will see is, you will see a technique which is used is you per kilo instruction or per 1,000 instructions. So what we try to do is we normalize the number of branch predictor misses, branch predictor correctly predicted, number of cache misses, cache accesses, everything is normalized to per 1,000 instructions that executed. So you can then compare two programs and say, hey, this one took this was 20 misses per kilo instruction. This is 19 misses or 18 misses per kilo instruction. So you can compare two runs that way. Otherwise, it's kind of difficult to compare, just raw numbers. Okay. So the key part when we do pre-silicon is we either use an emulator, which is done in hardware, or we use a simulator. I will be focusing more on simulators for this particular talk. So what does the simulator do? It models the system being analyzed. It models the pipeline, it models the cache, the entire core, the interconnect. Either we can model them separately, which means that you model the cache separately. You have the CPU pipeline, you have the pipeline, the fetch, decode. Each part of this is modeled separately, the entire pipeline, and then how it interacts with the cache is modeled separately. That's one way to do modeling. And there's another way which you always want to do is you also want to put them together and see how well does it do together. So when I want to look at simulators, this is what we want to do. We want to check how well they interact with each other. We want to check alternative designs. Like if I want to code in a particular algorithm for doing prefetching, I can code in that algorithm into the simulator. I can check two variants of that algorithm and check which one gives me better prediction. Okay, and we do the performance projections on standard workload. So we take the spec workload, we run the benchmark on it, and we run the benchmark on the simulator and see with a two alternative design which one does better. And we use the same thing again during verification of the hardware design. I will talk about that, the verification part a little more in a while. Okay, so two typical kind of simulators that we have is one is what is called a functional simulator. A functional simulator is where you want to check whether the hardware design is working correctly. I'm not worried about performance. I'm worried about correctness. Right? For example, if I have an instruction, if I added a new instruction, let's say I wanted, it's basically an instruction set architecture simulator. So let's assume I started a new instruction for which does AES or encryption. Then I want to make sure that programs that use this instruction work correctly or not. So I have a simulator which allows me, this helps also, BIOS designers to make sure that they can check their programs directly on the simulator first. Or application designers, they can check whether the program will work correctly. If you have, otherwise, how will they test? How will the compiler designer check whether the compiler is compiling and creating a correct AES program, enabled program? He has to test it and run it somewhere. So functional simulator allows him to do that. For example, if you have this add instruction, add R1, R2 at offset of 1000. So you are adding the content of the memory to register R1, right? So offset by, this is the base and this is the offset. So the functional simulator only keeps track of what will be the content of R1 and R2 after executing this instruction. If the value in the memory is 15 and the value in R1 is 20, then I must add 15 to 20 and I must get the result 35. That's the goal of a functional simulator. It needs to just keep track of the state of the system. Okay, but it does everything. Like what is input to it? Its input is the program itself, which means that it will cycle through the program, which means it will load the address into the program counter, execute this particular instruction, decode it, execute it, and then go on to the next. It does not do any performance study in this functional simulators. These are more used to check if the software stack will run correctly. If I will run a new instruction, will it compile and run correctly? Is that somewhat clear? Okay. If I have multiple processing units like CPU, GPU, TPU, and okay, how will you find performance of each unit? Typically, we will have separate simulators for each, and we will look for handover from one to the other, and then each one will run at separately from. That's how we kind of. We'll have to do some. See, simulators are costly by very nature. Like for example, if this was to run directly on hardware, it'll probably take a cycle. But if you're running a simulator which is trying to say, hey, I need to take the value in R2, put it in, add it into R1, store it in my state, it'll probably take close to 50 to 80 cycles just to do this. To do this, it's costly to do simulation. So your programs will be slowed down by 10, 20 times, 50 times when you're running it on this simulator. So you cannot simulate both the CPU and GPU together. You probably will simulate CPU separately, GPU separately, and put them together. Or sometimes even you can use an emulator, which is in hardware, which is a stripped down hardware, which mimics the basic behavior of the of the processor. Nikunj, does that answer your question? Okay, I hope so. Okay, good. The next type of simulator that we are looking at is a timing performance simulator or a cycle accurate simulator, what is called. In a cycle accurate simulator, what do? We take how long does it take to execute a certain set of instruction. So we are not so much interested in results per se. We are more interested in seeing how long will it take to execute. Yes, results become important at some point of time, but not at in this case. So these are called cycle accurate because we want to make sure that every time we run this, the results are not off by too many cycles. We compute total cycles. So in this case, we check if the location is in DRAM or is it in cache. If it is in cache, we have to move the data from cache to register. How long does it take to move the data from cache? We'll issue the fetch. How long does it take for the cache to respond to the request? We'll add that many cycles. Then we'll perform the add. We'll take the number of cycles for the add and track how much time does it take for us to compute this entire instruction. So this is very much the tool most hardware designers use for designing, for figuring out whether a particular solution at the microarchitecture level. This is what most hardware designers will use to check alternative designs. They will not go down to RTL. At this point, RTL has not been designed. So at this point, they will be only looking at saying that how can we try and mimic the latencies and all as close from what the RTL has. The RTL designer says this will be the latency. Take that, plug that into the simulator and simulate at the microarchitecture level so you get the results. It will be slow. This will probably be 1,000 times slower than running the actual program. It will take a few days to run this, a couple of days to run the entire simulation, but you will get the result. And the accuracy you want depends on what you're trying to use this for. So in academia, we tend to be a little bit less accurate, but in the industry, this needs to be really accurate down to the last less than 1%. So it needs to be really, really accurate in terms of, when I say accurate, how do we measure the accuracy? We need to make sure that the simulator is less than 1% away from what RTL tells me it will be. So we have one simulator for the microarchitecture level. We have one more, which is the RTL. So we will take the same application, run it on both short sequences, see what my simulator tells me is the time, see what the RTL tells me is the time, and those two should match. If those two don't match, it means either the architecture, my model is not accurate, my simulator model is not accurate, or it means that while designing, the RTL people have introduced some delays, which needs to be optimized of. So problem could be on either side. So they kind of tend to work together to make sure that the RTL is correctly represented in the simulator, and the simulator's numbers are correctly implemented in the RTL. So it works together to make sure how these two get more accuracy out here. Any questions at this point? Okay. So someone asked a while back, will the A.O program be directly run on, when I asked the question, they asked, is it run on RTL? Would we be able to run A.Out directly on RTL? Okay. That's a little difficult to do. Typically what is done is input to these simulators are provided by generating an address trace. We generate an address trace. We don't have all the complexity of decoding the instructions when we, decoding and running the control part. So what we tend to do is we provide an address trace which tells what instructions and data addresses are we touching. And this allows us to generate the address trace once, because then we don't have all this overhead of the functional part of the program. We just are trying to look at just getting which addresses will the processor be fetching from, and let the RTL run with that. Okay. This allows for repeatable results, and both the cycle accurate simulator and this will run off an address trace. And these traces we try and generate for standard real world applications. So most of the time when you see, even in the academic literature, you see simulators like Gem5 and all of that. We could run it from a tool like Pin, which generates these address traces. Is the concept of an address trace clear? So it's nothing but a dump of the program counter values. So what it's the interface between the memory and the processor. So the program counter sequences we will be dumping out. Any questions on this? So the question then arises, how do we really get the trace? So how do we get the trace? We use the functional simulator. So we run the program through the functional simulator, and the functional simulator then hands over these traces. Challenges are, of course, tracing through the kernel can be handling multi-core. If you have two cores and there are two programs which are executing close to each other, then how do you get a trace of both cores and run it through the simulator? This is a very challenging, very interesting area of how to get traces from multiple cores, how to improve the simulation methodology. Modeling and simulation is a very, very challenging area. How do we make sure that one sequence of instructions that we are capturing in a trace, is that really representative of the core application behavior? You cannot capture very long traces because you need to store them. They go run into gigabytes of data. So do we really trace the entire application? No, we only trace snippets of the application which we think are representative of the program. Now, the different parts of the program behavior which are representative. Then the research question that comes to be asked is, how do we know it's really representative? How do we know that we have moved from one phase of the program to another phase of the program? Okay. So these are all very interesting research questions, which is, how do we know that it's representative of the way the program runs? How do we know that it is it's in the same phase or it's in a different phase of the program's execution? How do we handle multi-core tracing? These are all very interesting problems, and both engineering problems as well as research problems out here that which people trying to look at. So with that, we kind of come to the end of the first part of the lecture, where we have talked about the performance analysis methodology. We talked about what the workloads are, what's a simulator, the different kinds of simulations. I hope that gave you a perspective of the process that's followed in both in the industry in many parts, and also where there are research problems that you can attack. Any questions? We still have. I think we started at 11:25, 10:25. We are now at 11:40. That gives us an hour and 15 minutes. So, any questions that you have, I can take up maybe in the next part, and then we talk about performance tools. Professor Vinay, is there? Or has it become too boring? You guys have gone off to sleep, too hungry. Okay, if there are no questions now, then we'll should we reconvene in about at 12 o'clock or what time? Am I audible?
Yes, 12 o'clock.
12 o'clock. Okay, then we'll reconvene at 12 o'clock, and we can go over performance tools. I'll probably be done by about, depending on the kind of questions. I think we had a very interactive session. Thank you, guys. So maybe we'll come back at 12, and by 1:15 we'll be done with that session. Thank you.